Hi everyone, welcome to the second of 4 videos going through some past exam questions, looking at the topics of rate concentration graphs and also some bits about the rate determining step. And we will get some of that in this question. There wasn't anything about the rate determining step in the previous video, but there is a part of it on this question. This question is very similar to the one in the previous video. Again, you can see we've been given a graph and we've been given some information in the table. And what are we being asked to do? Work out the orders of reaction, the rate equation, and the rate constant. Okay, so hopefully you're starting to get quite familiar with these types of questions. This is definitely a topic where you know what to expect in the exam. Okay, and you've got to make sure that you're comfortable with these questions. As usual, we're going to try to make sure that any conclusions that we make are linked to the data that they've given us. Okay, so first of all, we're going to have a look at this graph. Again, just check what the graph is actually showing you. It is a graph of rate against concentration. We've talked about concentration time graphs, so make sure you know which type of graph you're looking at. So we're going to say then from the graph, what can we see? What is this graph actually showing us? Well, it's showing us that when we change the concentration of the iodine, the rate stays exactly the same. Okay, so from the graph, we can see that the concentration of iodine has no effect on the rate. Therefore, the order of reaction with respect to the iodine is zero order. Okay. So changing that concentration has no effect on the rate. And hopefully you'll be able to recognize these graphs the more you practice them. As soon as you look at that, you can see this is not making any difference. Okay, then we need to have a look at this table to work out what's going on with the other reactants. So again, as always with these kind of tables, we want to find 2 experiments where the concentration of one of the reactants is changing, but the concentration of the other one is staying the same. So if we look here at experiments 1 and 2, we can see that the concentration of HCl stays the same. So we can tell something about this other reactant here. So here the concentration has doubled, and what has happened to the rate? The rate has also doubled. Yeah. So therefore, from experiments 1 and 2, the concentration of our reactant has been times by 2, and the rate is also times by 2. Therefore, the order with respect to this ketone is first order. Okay, then we need to do the same thing, but for the HCl. So we want to find 2 experiments where the concentration of HCl has changed, but the concentration of the ketone reactant has stayed the same. So we want to be looking at experiments 2 and 3, so that this has stayed the same. So we can see here what has happened to the concentration of HCl. We've gone from 2 times 10 to the minus 2 to 5 times 10 to the minus 2. So this has been multiplied by 2.5. And then if we have a look at what's happened to the rate here it looks a bit confusing. You think it's gone down, but you've got to be careful. Look at the powers of 10. It's 4.2 times 10 to the minus 9, and it's now the new rate is 1.05 times 10 to the minus 8. So it has actually increased. Okay. This is perhaps not obvious to look at straight away. So we can just do this on the calculator. Let's just do the new rate divided by the previous rate. Okay, so 1.05 times 10 to the power of minus 8 divided by 4.2 times 10 to the power of minus 9. We can just use that to work it out for us. Okay, and that's times 2.5 as well. Okay, so this question then carries on the other page. So if we fill this in here, we can then say that from experiments 2 and 3 we were looking at, my handwriting, the concentration of HCl was times by 2.5, and the rate was also times by 2.5. Therefore, the order with respect to the HCl is first order. Okay, once we've worked out all of our orders of reaction, we can then write the rate equation. So the rate will be equal to K, and then we're going to put in the concentrations of all the different reactants. If we go back, what conclusions did we make? We said that the I2 was 0 order, so that's not going to be involved in the rate equation at all. We said that the ketone reactant is first order, so that is going to be in the rate equation. And we said the HCl is first order, so that's also going to be in our rate equation. As usual, then we need to rearrange this. So we need to have K is equal to rate divided by the concentrations. And then we're going to substitute in some values. And again, we can choose the values from any of the experiments that we like here. So again, I'm just going to choose experiment 1, but it doesn't matter. Choose any experiment here. So we're going to have the rate as being 2.1 times 10 to the minus 9. We're going to take the concentration from here, 1.5 times 10 to the minus 3. And the concentration of HCl is 2 times 10 to the minus 2. And then we can calculate that. So 1.5 times 10 to the minus 3 times 2 times 10 to the minus 2. And then I'm going to do 2.1 times 10 to the power of minus 9 divided by the previous value. And we get a value of 7 times 10 to the minus 5. Talking about the values of rate constants quickly, it's not something that is predictable. Okay? Rate constants can be very small numbers, as you can see here. They can be very large numbers. It's not something where you can look at it and go, that looks really strange, I think I've got this wrong. It can be pretty much anything. You can't have a negative number, that doesn't make any sense. But other than that, there's no real way of knowing that you've done something wrong. Just check your calculation if you think you've gone a bit wrong somewhere. And then, as always, we can't have a number without any units, so we're going to substitute our units into the equation as well. So units of rate are moles per decimeter cubed per second, and then units of concentration are moles per decimeter cubed. We can cancel out one set of moles per decimeter cubed, and so then we're going to end up with seconds to the minus 1 over moles per decimeter cubed. So then we're going to end up with this is equal to being moles per decimeter cubed to the power of minus 1, and then we just need to sort the bracket out. So seconds to the minus 1, moles to the minus 1, decimeters to the positive 3. Okay, and so then we'll just write this as decimeters cubed per mole per second. So hopefully we're getting quite familiar with those kinds of questions now. You can see that the same types of questions do come up. It's just sometimes they throw in a rate concentration graph as well as just having information in the table. Now the second part of the question here then is our first introduction to something to do with a rate equation, a rate determining step, and a mechanism. So this is about a different experiment. So we're investigating the reaction of hydrogen and iodine monochloride. We've got an equation, fine, and we've got a rate equation. Okay. So what does this rate equation tell us? We can see that the H2 is first order and the ICl is also first order. It then says predict a possible two-step mechanism for this reaction. Okay, so they're saying that this reaction doesn't all just happen in one go. There are two separate steps. Okay. And it says the first step should be the rate determining step. Okay, and all this means is that the rate determining step is exactly what it says on the tin. Really, it's the step that determines the rate, right? The rate determining step is the slowest step of the mechanism. Okay. How does that help us? Well, if we've got more than one step going on, then anything that is affecting the rate of the reaction has to be involved in the rate determining step. Okay. And so there is a link here between the rate determining step and the rate equation. Anything that's in this rate equation is in the rate determining step, okay, because it's affecting the rate of the reaction, and so therefore it's got to be in both of these things. And actually more than that, the order of reaction tells us how many molecules of that substance, or how many ions if it's an ion, are in that step. So from the rate equation, because H2 and ICl are both first order, it tells us that the rate determining step must start with just one molecule of H2 and one molecule of ICl. Okay, so we've just literally taken whatever's in the rate equation, those are the reactants in the rate determining step, and the number of molecules is whatever the order of reaction is. Okay, so they're both first order, so one molecule of each. And you would get 1 mark for that. You can see this is a 2-mark question, so just that part of it gets you 1 mark. Everything else gives you the other mark. And so what we've got to do now is create 2 steps that add up to give us this reaction overall. Okay, and so where on earth do we even start with this? Well, we start with thinking about what the products of this could be. If H2 and ICl react together, what could it make? Well, it could make HI, couldn't it? But that's not one of the products that we're trying to make. Let's try and make the right products. Okay? Well, this is a reaction we're supposed to be getting out of these two. So can we make these products? We can't make I2 out of this lot because we've only got one iodine. Can we make HCl? Yes, we can. So let's make a molecule of HCl. That's the product we're supposed to get. And then what are we left with? If I've used an H, I've got HI left over. Okay. So we've kind of got to some of the right products, but not all of them. What do we do with step 2 then? Well, step 2, here we start to compare what we've already written with what the overall equation should be. The equation says we're supposed to start with H2 and 2 molecules of ICl. Okay, so far we've got the H2, but we've only got 1 molecule of ICl. So I need to have another molecule of ICl. So that must be involved in the second step. Okay. And the products are supposed to be 2 molecules of HCl and 1 of I2. And so far I've got 1 molecule of HCl, but not the other one. So this step must make another molecule of HCl. It must make the I2, because we haven't made that yet. And I've got HI in the products here, which is not supposed to be in the products. So I need to use that HI up. I need to get rid of that. So that must then be the reactant in the second step. And then we just need to check here, does this actually work? If I take ICl and HI, it can make HCl and I2, that's fine. What you should be able to see then from your 2 steps is that when you add these 2 together, you'll find that the HI cancels out. And you're left with H2 and 2 ICl, making 2 HCl and I2. Okay, so your first mark comes from this part, which you remember we said just comes straight from the rate equation. And then the rest of it is kind of building it up to make sure that the 2 steps together give you the overall reaction as it's supposed to be.